Hello, everyone. This is me, Ahmed Al-Garhi. I will be moderating this session today. It is always a pleasure to have Dr. Mehdi Azari with us. And today he will teach us something about PVT analysis. As you know, Dr. Mehdi Azari was a senior global technical advisor, retired from Halliburton after 32 years of service. He has more than 40 years of experience in the oil and gas industry, and has authored more than 100 publications with 15 US patents. He was previously a professor of petroleum engineering at the University of Wyoming and worked at OSCO Computer Center in Abadan, Iran. And also he is a member of SPE and SPWLA. His area of expertise are in reservoir characterization and fluids, as well as well testing, production operations, and optimization, gas lift evaluation, asphaltene remediation, pipeline, and choke setting, almost everything in oil and gas. Secondary recovery studied such as water, gas, and polymer flooding. Also, Dr. Mehdi worked like 6 years in Algeria, Saudi, and Kuwait. Thank you, Dr. Mehdi, for accepting our invitation. And now you can start.
Thank you very much. Good afternoon and good evening, the audience. It's my pleasure again to make you the third presentation in this series that is basically the Marietta College and SPE sponsored. And I want to also thank specifically from Dr. Ahmed Al-Garhi, because he put a lot of effort to get the teachers to start these kind of series for the benefit of students everywhere in the world. From last week that I was talking about decline curve analysis, I had a couple of examples that I wanted to share, but I think I forgot to do that. And we got about 1 hour, 15 minutes done, and then I just totally forgot to share this one. So I'm gonna start it with those two examples. There are two wells, A and B, that I have the production history for a few years, okay? So now we wanna apply the exponential decline to find out a lot of information that we talk about it, okay? So we first find out the decline rate, what type of decline it has, the remaining reserves, how many more years they're gonna produce, how much it's gonna produce to the economic limit. So this is the data for well A and for well B here. And the first thing that you do is you have the data sorted here. Production from this case is from November 1997 all the way to 2001, August of 2001. So Excel is an excellent platform for decline curve analysis because you can generate so many different types of plots. So you plot the data here. This is a semi-log plot, which is that the rate is a semi-log. And if you look at it, it looks like a straight line. This is well A, and this is well B. And so what you do, you try to come up with a type of plot. In this situation, we did it semi-log, and we were able to pass a straight line through that one, which is perfect. And so we start from that one. We know that let's say that December 1996, which is, I'm going to show you this one. This is better because that one was, the date is showing in days. So let me talk about well B. So this is January 98. I have that data, and you extrapolate it. It comes, you can just read the number. You can see, you can put your mouse over there and it tells you 130,000. So extrapolate 130,000. And then at the end of it, which is April 2001, which is this point, the other end of it. And if you put your mouse over there, it shows 33,270, which is, so you have the two ends of it. Then you have the date from here to there, okay? So you subtract the two dates from each other. That shows the subtraction is going to be 3.24. So I have 3.24 time duration, and then you apply the exponential decline equation here, which is shown here. And let me zoom a little bit. Maybe you guys see, I think it's better. I increase it by 10%. So you get the decline rate from the equation, and the decline rate is gonna be, this is that 3.24, the duration, huh? So you get the entire length from here to there, and then during that time, average decline rate is 0.421 per year, okay? So now, once you get that one there, then you just plug it into the equations. Then find the remaining reserve. So number one was find the decline rate, which is, we found it to be 0.421. Number two, find the remaining and ultimate recovery if I produce it to an abandonment of 3,000 MCF a day, per month, because these are per month, all right? So now the remaining reserve is, this is the equation, the current one to the abandonment, and multiply by 12 because these are monthly. The D, the unit for D is per year. So right now at this point is 33,000. Remember there was 33,270. So you put 33,270, and then abandonment rate is 3,000 MCF per month, multiplied by 12 to make it per year, divided by the decline rate. It gives you the remaining reserve is 862 MCF. Okay, so that means the remaining reserve is 0.863 BCF. Then the cumulative recovery is how much they produce from time zero until this time. Okay, that's 2.28. So the total recovery from this well is going to be 2.28, which you already produced, plus 0.83, which is the remaining. So the ultimate recovery from this well is going to be 3.143 BCF, billion cubic feet, which is not bad. I mean, you want it to be like 6-7 BCF to be but it's not bad. It's not typical for wells, gas wells in US. Then find the remaining life of the well. You use the same equation, exponential decline equation. You solve for T, and then this is the, once you get to 3,000 from this day, which is 33,270, divided by the decline rate, time is 5.7. So 5.7 more years until production goes from 33,270 to 3,000. Okay, very simple Excel spreadsheet type of work. Okay, Dr. Ahmed, should I wait until the end to ask this question, or do you want me to ask? Do you want them to ask questions about this Excel spreadsheet? It's not a big deal. I mean,
all questions will be at the end.
At the end, okay. So today I'm going to talk about the fluid property PVT. Again, the PVT that I present, part of my schools that I teach, takes 2 days. I spend 2 days. There's so many sections that I'm not talking about, like asphalting. I'm not talking about any hydrate formation, how to prevent hydrate formation, how to do at the wellhead stuff. There's a lot of those that needs to be considered. So I cut a lot of those there to just make it but the right size. And let's see if I can. I wanna just bear with me one moment. Okay. So this is a typical shape of the thick blue line is called a phase envelope. There's a phase envelope. I mean, it has different shapes. Some of them are like this, some of them are flat, depends on the profit that you have. And then inside, on this phase envelope, there is a point here called critical point. This is very important. To the left of the critical point, you have oil. To the right of the critical point, you have gas. Again, now where it is located is also important. So if you have oil here, close the door that we do not get any noise from outside. So let's start with this oil. This is called bubble point. For the oil part, it's called bubble point. So I'm above bubble point. Above bubble point, that means the gas, which is in oil, is dissolving. Okay. So now you drop the pressure. This is a pressure curve. This is temperature curve. You drop the pressure isothermally inside the reservoir, because inside the reservoir temperature doesn't change. Pressure changes by production, but not temperature. So temperature drops inside the reservoir up to a point that you get to a point called bubble point. You get to the bubble point curve, and the bubble point curve is a point where gas starts to come out of the oil, because you reduce the pressure. Oil expands. Why? Because you drop the pressure. It expands. You increase pressure, compresses. You decrease pressure, it expands. It expands to a point that gases start to come out of it. That is the bubble point of that oil. The bubble point could be very low, could be very high. We're going to talk about it, which cases is higher, which cases is lower. So inside the reservoir, once the bubble point happens, and then you drop the pressure, you get more and more and more gas, okay? So these dashed lines here are the percentages. So here is like 10% gas, 20%, 30%. If I just want to guess, this is my 50%, like 60%, so probably like 56% gas. These are roughly. But the same oil, when it is coming through the tubing to the surface and going to the separator, that oil will cool down. So not only pressure drops, but cool down. But as it is coming down, there's a lot of drop in pressure. I mean, your separator pressure could be 100 PSI, 150 PSI, something in that range. Your reservoir oil here could be 4,000 PSI. You drop it to, let's say, to 2,500 PSI. But here you drop it to 100 PSI and it is cooler. So now you can see there's a lot more gas coming out of that separator. And eventually, from that separator, you send it to a stock tank and all the gas comes out of it, all right? Because now you drop it to atmospheric condition. So this is called the oil part, which is liquid. To the right of the critical point, you have gas. Now you have different types of gas. And the curve from critical point all the way to right is called a dew point. Similar to oil, you could have a gas here, and then you would drop the pressure, it gets to this dew point. And now, because it's gas, the gas is expanding, there's some liquid in that gas. That liquid, which is called gas condensate, which is very light, very high apical gravity, just comes out of it, as you can see here. So if you have a situation here, like this one here, that gas produces oil in the reservoir, this is called gas condensate. If the gas, as it drops in the reservoir, stays in the gas zone because it's to the right of it, anything inside this phase envelope, inside of this phase envelope, you have two phases of oil and gas. Here is more liquid. So here is gas coming out of oil. Here's more gas. Basically, oil is coming out of gas. You could have a situation that you only get 10%, 15%, 20%. And because that the liquid has higher mobility, because if you talk about the affinity or the willingness of the liquid to stick to the rock, usually it is water wet. So water starts to stick to the sand. Then it is oil. The last one is gas. Gas is the most undesirable fluid to stick to the rock. So it dries. So if this is the rock, and then there's a layer of water, and then there's a layer of oil, and then gas goes in between there. So now if your oil increases, it blocks the gas. You're not going to get the gas flow. Some of these wells, especially unconventional wells that I was dealing with, a lot of in Saudi Arabia, there are gas condensate and there are tight formations. So if you let the liquid, if you let the pressure drop from here to here, then that liquid comes out of solution, goes into those smokers. Unconventional means very, very tight. It's going to plug all of those holes with liquid, the liquid that came out of it, we call it, which we call it condensate, and then it's going to block the gas. You're not going to get any gas flow. And suddenly pressure drops, suddenly you lose pressure, and the well is dead, just like that. So in an unconventional way, you got to be very careful not to drop it. So understanding the PVT is very important on how to produce it, how to effectively produce it. So one of the first things that we do, but in those situations, the formation pressure is very high. Formation pressure is like 9,000, 8,500, and then the dew point could be like 5,000. But believe me, you drop some of that liquid into a tight formation, you're going to have 4,000 psi pressure drop in the formation. So if this is the formation and then this is the wellbore, pressure is let's say 9,000 and it's going to drop so sharply to 5,000 here. And then this area is okay. And then if it is 5,500 here, so from where it goes below 5,500 around the wellbore, you're going to have basically a liquid bank, which is blocking the pores. And that's the area with the smallest cross-sectional area for the fluid to flow. Because when the oil or gas is out there, they're coming here, they're crossing a bigger circle. As they're getting closer to the wellbore, the same volume is crossing a smaller area. And then if this smaller area is filled with liquid, which is gas condensate, the gas cannot come out. Your pressure drops a lot more in around that area. So management of the oil reservoir, gas reservoir, hydrocarbons, very important to know what type of oil you have, what kind of reservoir you have, do some modeling before that and find out that, especially there are some correlations, we're going to talk some of them about it, that what is the dew point, what's the bubble point, and you need to manage it. So now if that gas condensate is coming to the surface, same story, temperature is going to drop, pressure is going to drop, you're going to end up here. Now, if I can manage that gas condensate to bring it out of the reservoir into the wellbore and then it drops in the wellbore, it's okay. I mean, it's better to oil come out of it when you get to the surface, but it's impossible because as it is coming to the surface, you have to have a drop. A fluid flows from a high pressure to low pressure. So if I don't drop the pressure, you're not going to have any flow. So you need to have a pressure drop for the flow to happen. Okay, but if this event, which is getting below dew point, happens in the wellbore, it's okay. If it happens in the reservoir, it's not okay. All right, so this is the management for gas reservoir. Then we have another one, which is called a dry gas. A dry gas is way to the right, that it is purely gas. And then you inside the reservoir, pressure drops, comes from that point to this point. All right, that point to this point, and it is gas. It doesn't cross the point. And then you could have a situation that it is dry gas in the reservoir like that one here. And as you produce to the surface, go to the separator, you do not have any, it doesn't pass this dew point. So pressure and temperature is high. So we call it dry gas. But as it is coming to the surface, it might pass through some of these situations. That is called wet gas because it produces some liquid with it. Now, some of this gas, so if the point is this gas condensate of being here, if it is here, and then just follow my mouse, if my gas condensate is somewhere here, it comes down, pressure drops down to the dew point, and then the first drop of liquid appears. If you drop it more and more and more and more, all the way more here, so I get to 100% gas, to maybe 98% gas, and then I get to maybe 10% liquid and 90% gas. Now, as you pass that plateau, the liquid gets dissolved back into that gas. So now from this 90%, you get to 92, 93, 95, and then you go back to 100% gas. And then you come down his gas. And that's why we call it retrograde condensate. So retrograde condensate or gas condensate, there are different definitions. So this is very important. That's why I spent time on this one to make you understand difference between gas condensate, dry gas, and wet gas. All right. So now there's a little bit more classification. So for the oil, you could have a black oil, and then if it is in this area, it could be asphaltene. We're not going to get into those here. Black oil, then you could have as you get close to the critical point, you could have a volatile oil. Then there's an area above the critical point, which we call it critical fluid. It works like a gas, but I mean, it has a very different phenomena. Then to the right of that is gas condensate. Then you have a lean gas condensate, which is gas condensate, but doesn't produce a lot of liquid, just produces a little bit liquid. And then gas, wet gas, dry gas. Sometimes when the fluid is to the left and to the right of this critical point, like a volatile ore or a gas condensate. Sometimes it's difficult to recognize what it is. Is it volatile or is gas? Because they have very similar properties. But with this difference that to the left of this one, you're trying to produce a liquid, okay? The gas that comes out of it is not a lot compared to here. Here is all gas and what comes out of it is liquid. As long as you have high permeability, it doesn't matter. There are some wells in the Persian Gulf that Saudi is producing, and they're producing 100 million a day gas condensate because the permit is high. There are some gas in the South War, gas condensate in South War, that if you produce like 20 million, that's very good, okay? That's very good. 20 million is very good for that one. Now, if you look at the reservoir, this is a reservoir, this is a wellbore, this is the 8,000 feet into the reservoir, okay? And this is pressure scale. And this is the brown is your bubble point or dew point. If you have a 100 millidarcy formation, pressure drop is not significant. You don't see much pressure drop. For a 1 millidarcy formation is this reddish brownish curve. So you can see there's more pressure drop around the wellbore. As I said, as you're getting closer to the wellbore, the cross-sectional area gets smaller. So now your pressure drop increases. And then the green is a low permittivity, like 0.2 millidarcy. You can see that right from beginning, as it is producing 0.2 millidarcy, it causes a lot of friction, a lot of pressure drop, and drops the pressure to 3,000. So what the formation permeability is makes a difference on how you produce it. For instance, this one, I can produce it at very high flow rate here. Same with this one, but if permeability is low, I cannot because I do not want to go to low bubble point. Okay, if it is oil, that gas which is dissolving is like an energy dissolving the oil, which just pushes the oil out. Huh? It just pushes the oil out. So I want to keep that that gas in solution. All right. There's in Kuwait, they have a sandstone above the limestone called water zone, water reservoir. Pressure is around the dew point. It's oil, and they're not producing that one because it's around bubble point. They're doing some water injection from the periphery of the reservoir, from the outside, to raise the pressure inside. So they're not producing. So they're making sure that when they do hydraulic fracture on the carbon reservoir below that one, it doesn't go to water. Because if it goes to water, you're producing from water because the water is very high permeability, sand, and you do not want to produce that one because now you drop pressure. So if you drop the pressure more, you cannot produce any of that oil because that gas is the energy for production, all right? So there are some of these classification that I have put here. For instance, if you have a tar or bitumen, it looks like a solid or liquid or very heavy, huh? Very heavy. And you can produce it to surface as liquid. The API gravity is less than 10. And this is the equation for API gravity for those of you who do not know it, which is 141.5 divided by specific gravity minus 131.5. And if you solve for that, the gamma, which is specific gravity, you get that one. The API gravity, the density or gravity of water is 1. So this is 1. So 141.5 divided by 1 minus 131.5 is 10. So the API gravity of water is 1. So you can use that as a reference. Oil is lighter than water. So if gamma is, let's say, 0.8, if gamma is 0.8, this is going to be more, and then it's going to be higher. So you could have an API gravity of 20, 30, 40, 50, depending on this gamma. The lower the gamma, the higher the API gravity. All right. Now, you can use this one as a basis. Once you hear API gravity of 10, that's water. If it is close to 10 to 15, you can say it's heavy. Once it goes to higher, I'm going to show you these numbers. But so that's the range. So the higher the API, the lighter the ore. So the tar bitumen could have API gravity of less than 10. So that means it is heavier than water. The heavy oil is liquid, produces liquid. API gravity could be between 10 to 30. Okay, and there are some wells in Venezuela and south in that area that I have dealt and traveled to those areas. The oil gravity is like specialized like 12, 13, 14. The gas oil ratio could be like 5. That means for each barrel is only 5, okay, which is very low. So the initial GOR for some of these heavy oil is less than 0.1. This is 1,000, huh? So less than 1,000 SCF per stock ton barrel, because I'm showing the unit of M, 1,000 MCF, 1,000 SCF. So the reverse of this one is called the condensate gas ratio. So gas oil ratio or condensate, so this is 1 over that one, all right? Then you have black oil, which is low shrinkage. It is liquid, and the API is usually less than 45. All right, and then the gas oil ratio could be less than 2,000 SCF per stock ton barrel. Then you have a volatile oil, which can come as like a liquid or vapor. Some of this volatile oil, you touch it, it is like a gas. It's like a vapor. It's so light. The oil in Algeria is of that kind. It is lighter than water. I mean, the viscosity is very low. Viscosity could be like 0.25. Viscosity of water at surface is 1. So this guy has a lot of gas in it. That's called a volatile oil. The API gravity is 45 to 60, all right? And the GOR could be between 2,000 to 6,000 standard cubic feet per stock ton barrel. Then you've got the gas condensate, that it is gas or vapor in the reservoir. And there are some oil that gets produced, and that's called condensate, or is a liquid. And then the API gravity of those is between 48 to 60. 60 is very light. And then the initial gas condensate ratio could be 5,000 to 6,500. But look at these two. The volatile oil could go up to 6,000 or maybe slightly over 6,000. The gas condensate could start from 5,000. So you see that these two are very close. So you got to know what type you're producing. Then you got wet gas. Wet gas in the reservoir is gas, and the API could be higher than 60, 60, 65. The GOR is 65,000 to 100,000, all right? And then you got dry gas. Dry gas is the GOR is 100,000 or higher. Sometimes I've seen 200,000. So 200,000 cubic feet per 1 barrel. So still you can see you could have a very, very dry gas, but it still produces some oil for you. Okay, all of these guys, the oil produces some gas, the gas produces oil. This is another specification here in terms of the density. Once the gas is inside the wellbore, and then you get the gradient. Remember before I was talking about as you're coming up, you take a pressure here, you get the pressure here, pressure there, you plot it, and then you can then get the gradient. So now you could have a gradient of 0.001 to 0.2 psi per foot, that's gas. The fluid density of that one is 0.14 to 29, these are pound per cubic feet. In gram per cc is gonna be this low, huh? Up to 0.46. If you could have a condensate from 0.2, the gradient would be 0.2 to 0.25. And then the fluid density is gonna be 29 to 36. And in terms of gram per cc, 0.46, 0.48. Typical oil has a gradient of 0.25 to 0.41. And the density would be 36 to 59.5 pounds per cubic feet. And the water is going to have a gradient of 0.4, 0.490. The fresh water at surface has a basically gradient of 0.433 psi per foot. Okay, and then the fresh water has a density of 62.4, but inside the reservoir, inside the wellbore, temperature is higher, so it could be a little bit lighter, 57.4, and it could have some a lot of salt dissolved in it. It could go up to 71 pounds per cubic feet. So that's a range in the gradient, that's a range in density. and this is the range in basically density in gram per cc. But again, fresh water is going to be 1. So fresh water is going to be 0.433 here. It's going to be 62.4 here, and it is going to be 1 here. And these are again the equations for API and specific gravity calculation. There's another classification of unitar, and for black oil, and condensate is 40. Let me bring it here. Condensate, move my, okay. Condensate is between 40 to 52. Light oil is 30 to 40. Medium is that. Heavy oil, look at 10 to 20. Extra heavy, now look at this one. Extra heavy oil could have an API gravity of less than 10. Okay, now the bitumen in Mexico, which is some sort of basically asphalting, the API gravity of the heavy oil in Villahermosa is in the range of 4 to 6 API. Anybody from Mexico, Villahermosa, I've been there, they have big mosquitoes. The mosquitoes in Villahermosa are really big. But remember this one, 4 to 6 API. Remember the API for water was 10. So this is pretty heavy, huh? You drop in the water, it goes to the bottom. It's like a solid, huh? And once you have this kind of heavy oil, they inject a steam to produce it. And then they truck the oil to refinery. They don't, it doesn't flow into the pipeline, huh? So they have to truck it. Okay. Now the other thing that you got to know is the phase envelope changes with production. So now I have 3 different phase diagram here. This is initial condition. After time 1, after time 2, things will change. All right. So don't think that once you have the same thing, it's going to stay the same. The phase envelope will change with time. Not only that, but also the critical point will change. So it could be here, and then could be here, or could be there, stuff like that. And then this is for an volatile oil. Now, these are the samples that I asked to be taken from one of the wells that I was monitoring. And this is called a volatile oil with an API gravity of 51. 51, huh? It's very high. The gas gravity was 0.73, the GOR is 4,000. So it's not very high, huh? Compared to this API gravity. I mean, you think it's going to be like 5,000 or 6,000, but then 4,000. Look at the color of the oil, huh? It's like orange. Now, the same well, after a while, because we're monitoring, we're cleaning, producing, it got to condensate oil. API gravity is 47.5. You can see that the API gravity was 51 with that oil because it had a lot of gas. And now the condensate part of it, which means you take the oil, the gas out, the condensate part of that is 47.5. Look at the change in color. It's like a dark brownish. Now it is light. Now that dark brownish could have some other impurities in it. I mean, we do not know. So there could be some other impurities. I have the PVT analysis. So now the same reservoir, look at that. Now it's like a olive oil. This is the same oil. This is the same oil. Started with volatile oil, 51 API, went to condensate at 47.5, and then went to a condensate with higher API gravity. So now this is like a clean oil. So you keep producing around the wellbore as you're producing, because there's some of these mud that you're using to drill, huh? And the mud has some oil in it. That oil has affected the type of the oil that is producing at the beginning, and then it's cleaning, and then finally you're producing this guy. This oil is pure. I mean, you can just put it on your car and drive, huh? This is like a 50, almost 52 API gravity. It started from 46, and now it is at 54. So that means I do not have a picture of that when it got to 54. But this is when we tested, it was 51.8. So now the downhole density measurement gets affected by floating fines. You can see this is one situation. You can see that, huh? There's some fines here, there, and that increases density. So you got to be careful when you take the density. I'm showing you some ranges for composition, and this is black oil, volatile oil, condensate, and this is gas. Look at the methane content. The methane content is very important. 48.8, 64, 87, almost 96, okay? So this is one component of that one. The other component, so methane, ethane, propane, butane, pentane, hexane, and keep going, huh? And then C7 plus is anything heavier than 7 added here. So again, the percentage of the C7 plus is also important. Look at that, 42, 15, 4.4. So if you just look at the composition here, you do not know what type of fluid it is, you know that this is gas, huh? Because of 96% methane, very low amount of C7 plus. And then here has a good percentage of C7 plus and low amount of methane. So now we need to have C7 plus molecular weight of the heavy end. The gas oil ratio, 625, 2000, 18,000. Look at this one, 105,000. So if I ask you a quiz here, this is a dry gas. Remember, dry gas was above 100,000, 100,000 and above. So this is above 100,000. And then this is 18,000. It's gas condensate. Gas condensate to wet gas, but this is gas condensate. Liquid gas ratio, which is reverse of that, is the gravity is 34 gravity, which is not bad. 34 is a good oil. 50 is volatile oil, which is very high. 50, almost 55. 60, 61. If you look at the color, this is green to black. This is orange, pale, red, brown. So this is the one that I showed you, the first oil that I showed you the picture. This is light orange, straw or olive. This is that gas condensate, the condensate that I showed you. And then the gas, if it has any oil, the oil is going to be like a liquid, like water. It's going to be clear. And I got it from Kraft and Hawkins' book. Now, this is another situation that I put the different oil from different parts of US. Again, we look at the methane here. Look at the Wyoming oil, has only 1% oil, 1% methane. And South Louisiana has 65% methane. And then there's a lot of other things. And then saturation pressure. Saturation pressure means like bubble point, huh? The bubble point. The one that has the highest gas content, methane content, has a very high saturation. That means at 4,730, the gas is going to come out of oil, huh? But the Wyoming, because it has very low amount of methane or other gases in them, you have to drop the pressure way, way down to get the gas come out of it. So now you can see a correlation between these guys, methane and the saturation pressure. And then look at the GOR, gas oil ratio. Again, very, very similar. The GOR of this one is 4,000. So there's 4,053 standard cubic feet of gas per each barrel of oil. And then this one has 22. So this is, again, directly related to the methane content, okay? And then formation volume factor, which is, we talk about it, is basically if I have 1 barrel of oil at surface, 1 barrel, I take it to the reservoir, what happens to that volume? If it increases, which will increase because the gas goes into solution, then volume is going to be high. So this is 1.03, that one is 3.6, that's very high. That means 1 barrel of this oil at surface is going to have almost 4 barrels inside the reservoir. Whereas for this one, it's going to be just slightly over. 1 barrel of that is going to be 1.03 barrels. Okay? We're going to talk about this later on. And then the API gravity, obviously this has high API gravity, this has the lowest API gravity. All right. Now this is another composition that I was able, I mean, this is one of the cases that they asked to be analyzed. You can look at the C1 methane content. This has a 66. No. This is not that one. I didn't do this one. Same story. This one has a lot of information. Why I put this one? Because I want to use this example for some of my calculation, bubble point calculation, GOR calculation, stuff like that. So now these are in bar, in basic metric, and I put next to that in fill unit. So this is PSIM GOR 62 met cube per met cube, but I brought it into a standard cubic per structure, and then I calculate the APR. I'm going to just use this example. And then you might have heard about LNG, LPG, NGL. LNG is liquefied natural gas, which is basically C1. LPG is liquefied petroleum gas. So that means the first two are liquid, huh? Actually, all of them are liquid. So C1 making it liquid. So that means you're exerting a lot of pressure. Liquid petroleum gas, C3 and C4. This is LPG. I mean, the ones that in the past, we used to have these big cylinders. Still you have it. I mean, some of these cylinders you go for picnic and then it has gas in it. That's LPG, huh? That's LPG. Then there is another one, NGL, is a natural gas liquid, which is basically the condensate that they have. Is a combination of C2, 3, 4, 5, 6, stuff like that, that they compress it into liquid. So now we start especially with oil, gas, water, stuff like that. So oil properties. So now we have fluid sampling. How to sample fluids? You need to have you take a fluid sample, you take it to the reservoir, you analyze it, get all the information. So now I'm taking that fluid to the reservoir, to the lab. That fluid should be a representative of the reservoir. So now the best technique is that I have some tools like these wireline tools, wireline sampling tools that we can send down, and then they have a bunch of different bottles. The one that Halliburton has is like 1 liter bottles, series of like 3 here, 3 here, 3 there, and then you can stack so many of them there, depending on how many of these they want. They sample it, they clean it, they have a density measurement downhole. Once it cleans, then they drop it to those bottles, they pressurize it, and then they close it. So now you have collected the pressure under reservoir condition, okay? Because once we come to the surface, the gas could come out of it, will come out of it because as you're producing it. And then that oil is not the same oil, it's because some gas has come out of it. Another possibility is that you go to the separator and then take the oil and the gas, and then you see from the separator what is usually the production. So production is, let's say that you're producing 1,000 barrels per day, and then you're producing, let's say, 1,000 MCF. So that's the ratio, okay? But this is not exactly all the time, because sometimes, my experience, sometimes, especially in these unconventional wells, you have the oil and gas coming here. You could have a ratio of, let's say, 800 standard cubic feet per sucked-down barrel. Another time could be 2,000. Another time could be 500, because it changes. Because they do not come all together, especially in these tight and unconventional, and especially when you have gas condensate, because as I mentioned, you get a liquid dropout in the formation, and that liquid dropout, if it's a small amount, is okay. But that liquid amount is gonna modify how much you're producing. And then the flow rate that you're using is important, because you got, this is your well bore. At the bottom of the well bore, you could have some water standing there. And then you could have oil standing there, and then gas comes out of it. You could have a horizontal, because the horizontal it's not really horizontal. Let me put it this way. So this is my horizontal well. It's not horizontal. Sometimes it's like this one. And then it comes here. We had cases. These are true cases. These are not theory. These are true cases. The water was sitting here. This oil is coming here, and then it needs to go up there. The water is standing here. This is the gas with gas condensate. So the gas has to come through that one. Not only that, but you're using some propants for perforating. The propants is sitting here. So there's a separate technique that at what rate I should produce that I can get rid of this oil, this water, this propant, sand, okay? Once you clean that one here, then you can have more like a steady state flow. Then it is more representative. So there's a lot of things happening. And then this is the well bore on the vertical part. If you're not producing at high enough velocity, the oil could go up there and then slips on the side of the tubing. And then the gas can can easily escape. Huh? The gas from the center of that, from the center, gas goes there, oil is sticking there, and then if you do not have very high velocity, oil could slip back. So any of those conditions, you could not have a representative fluid samples at the wellhead or in the separator. Okay. So now the oil, because we're talking about oil. So this is your bubble point here. This is called undersaturated oil. Once it goes below bubble point, here is called saturated. Okay. And then, as I said, once it comes to through the tubing to the surface, you have a separator which is at the lower pressure and temperature. So you could have separator here, but the reservoir could be at that point. Now, I need to explain here, why do we call it undersaturated? Because when I was a student, I was saying, wow, I have more gas here. Why it is undersaturated? I got less gas here. Now, the point is that the oil which is here has gas in it. So this is oil. If I drop the pressure just 1 psi, gas will come, more gas comes. If I add the pressure by 1 psi, increase the pressure, more gas is gonna do. So it is at the saturation. Just change the pressure, gas comes out of it. But over here, all the way from this point to get to here, no gas comes out of it. That means I didn't have enough gas to get dissolved in it. That's what we call undersaturated. So this is the way to understand it, that this is called undersaturated, saturated. All right, okay? Don't get confused. So now, if I have, let's say, 1 barrel of oil in the reservoir, I bring it to the surface, the volume of oil shrinks because part of that was gas. The gas was dissolved here. Shrinks, and then I got a lot of gas coming out of it. So this is separated. Then I take the gas out, and then I have the oil. From the separator could be anywhere between 50 to maybe 200, 300 psi pressure. So now I drop it to, sometimes we have 2-stage separator, but anyhow, at the end you put it a stock tank. Stock tank is supposed to be atmospheric, so more gas comes out of it. And then you can circulate this gas into this gas. So as you can see here, concentrate on the oil. Oil in the reservoir has more volume than separator than at atmospheric, all right? So if I have 1 barrel of oil, I take it into the reservoir, that barrel of oil is gonna have higher volume. The ratio of this volume divided by this volume of oil is called formation volume factor. Remember the one which was a light oil was 3.8 or something, 3.6. That means if it is 1 barrel here, it's going to be 3.6. The light oil from Wyoming, I think it was like 1.05. So if it is 1 barrel here, this is going to be 1.05 because it doesn't have much gas in it, all right? Now, bubble point pressure, the bubble point pressure, So there are some equations for that, and is a function of temperature, is a function of how much gas is dissolved, gas gravity, and okay, this is number 24. This is actually supposed to be gamma of the G, and you change the font and you make all of them Arial, suddenly symbol changes to G. Okay, so it's gamma. And then the bubble, this is, I mean, the different equations. This is one of the equations that is actually, I tried this very good equation, 1.2 times 1.89, gas oil ratio divided by gamma of the gas, multiplied by 10, API divided by temperature, minus 243. And remember that example that I showed you here earlier? Yeah, this one. I used the data for this case, all right? And plug the numbers. I didn't have gamma G on that analysis, so I put roughly 0.75 for the gas. API was 33, temperature was, now this is in degrees Fahrenheit, all right? It comes to be 3550, sorry, 3560. The one that was measured in the lab was 3560. This is excellent agreement. So this is a correlation, and this is actually measured in the lab. This is very good. I mean, 3560, 3568. Okay, so this is from that, the slide number 16 at temperature gamma G. All right. So that was what bubble point calculation. The next thing is the solubility. Remember undersaturated and saturated here. If I'm plotting pressure on the x-axis and then gas solubility in a standard cubic feet per time barrel here, and this is your reservoir, in the reservoir. You're above, this is your bubble point pressure. You're above bubble point pressure. Remember the phase envelope? You're above the phase envelope, you drop the pressure, but this is a different representation of the same event. So now here is pressure. You drop the pressure, nothing happens until you get to bubble point. So the amount of solution gas doesn't change. You get to the bubble point. From that bubble point down, you drop the pressure, more gas comes here. So as I mentioned here, this is called a saturated oil. So this part is saturated oil. And saturated oil could be all the way down to basically when there's no gas, all right? You can drop the pressure, you can drop pressure, more gas comes, drop the pressure, more gas comes, and so on. So this area is called saturated oil, this is undersaturated. Now there are different empirical equations for RS, which is solution gas flow ratio. Standing is the old one, and no, you've got to remember that each one of them was based on a certain oil. Standing has done a lot of work, but most of it is in California oil. Vasquez and Beggs, Glassos, Marhoun from Saudi Arabia. He has also very good correlations. I like his correlation, especially for gas condensate. And calculation of dew point from gas condensate from Marhoun is very good. And then Petrosky and Farshad. Farshad is my friend, was at LSU, University of Louisiana, is my friend. They did also some work on this RS calculation. And then again, I'm putting some equations like standing correlation. This is a standing correlation. There's an X here. X is defined by API temperature that. And then this is another correlation, which is pressure, gamma G, API, temperature, all right? So different correlation. Now there's next thing is formation volume factor. Remember, formation volume factor was the one that if I have 1 barrel of oil at surface, I take it to the reservoir, what would be the volume? Okay, that's your BO. So now let's just start at bubble point. At bubble point, remember, bubble point is the point that you have the maximum amount of gas in solution. If I go above bubble point, I'm not going to add more gas. The gas stays constant, all right? That's the definition of bubble point. So this is bubble point. This is pressure, temperature. Pressure here. This is BO formation. So now, if I go above bubble point pressure, that means I have the maximum amount of gas in the oil, and I'm going above that. So that means I'm compressing it, high pressure compression. So I'm decreasing the volume, and that's why it is declining. Remember the shape of RS? RS was, you get to the maximum, it doesn't change. Don't get confused between this. So RS was going up, RS going up, and it stays flat because this is the amount of gas. But this one is volume. Volume shrinks above bubble point, but it shrinks as liquid. So you're compressing liquid. But once you get to bubble point, you go below bubble point, is not only liquid, because now you're losing gas. So the volume quickly drops. All right. So this is again one equation for BO. I mean, you search around, you look at the petrometry handbook, you can find a lot of different equations for BO. The other one is called compressibility. And let me just bring it to par here. Okay, so definition of compressibility. If you remember on the well testing part, I talk about it. I like this equation a lot because it has a lot of application. Compressibility is equal to minus 1 over volume, partial V, partial P. That means if I increase pressure by 1 psi, and I have a certain volume, what percentage of the volume increases? That's this equation. You just, in the lab, you compress it, you just see how much pressure goes on, then you can get compressibility. It's that easy. If you write this equation in terms of BO, because BO is also volume, you get this equation. If you write in terms of density, because mass stays constant, if you multiply by mass, then you can convert it to density. So this is a above bubble point, which is a single phase liquid. If you go below bubble point, now you have two sections. One is related to oil, which is this one, huh? One is oil, which is this part. The other one is related to gas. So this is the part related to gas O ratio, Bg and Bo of the gas, formation one factor of oil and gas. And then now let's see what we can do with this equation. I'm not sure whether we did a similar example before or not. So let's say you got 1 million barrels of oil in a reservoir, pressure 6,000. You produce the 10,000 barrels of this oil, and the oil compresses 4 times 10 to the power minus 6, psi minus 1. Usually for the oil is like between 4 to 10. If you have a lot of gas, then it's going to be 10. For water, it's roughly about 3.5 times 10 to the power minus 6. Rock, if you do not know it, you just use 3 times 10 to the power minus 6 for rock. And then you want to know, if I produce 10,000 barrels out of this million, what would be happen to pressure? So you use the same equation here. If you call it delta V, delta P, so you solve it and you get this equation. CV delta P is equal to delta V. And then this is C, volume, pressure 6,000 minus current pressure is equal to 10,000 produced. You solve for that one. So pressure dropped to 3,500. All right. So 1 million barrels of oil in a reservoir, assuming that this is only oil, huh? This is very simple because there's no water, no gas, nothing. So if it's only oil, reservoir pressure 6,000 drops to 3,500 if I produce 10,000. Now, this was for CO of 4. For this, everything else is the same. If CO is 10, that means more compressible. Then I solve it. Pressure that right now is only 5,000, so it's a lot higher than that. So you can see how important that compressibility is. Initially, when you're producing from an oil reservoir, initial decline is only related to the compressibility. If you're doing material balance, if you're doing a simulation, when I was in Algeria, I was helping one of the graduate students who was working with me to put together a simulator. And then because he had the data and he was not able to match it, I said, just work on this compressibility at the beginning, and he was able to, so he played with the number for compressibility until he matched the data. Okay. Now, oil gravity and density, and this is the equation that we have for API and gamma. Similar with that, I can just play with these numbers a little bit here. Gamma, which is specific gravity, is going to be raw oil divided by water. So oil is, the gravity is determined with respect to water. Gas is referenced with respect to air, okay? So oil is, we all the time want to know how much that oil is lighter than water, okay? So if water is 1 gram per cc or 62.4 pound per cubic feet, and then or 350 pound per barrel. So these are different ways that you can show it. And so rho of the oil, density of the oil is going to be 350 gamma oil, and the unit is going to be pound per barrel for 1 barrel. Huh? You could come up with the same equation in terms of pound per cubic feet if you use this equation. So it's going to be 62.4. Or rho O is going to be equal to gamma O times 1 gram per cc. So depends on how you want to get it. Now, what is viscosity? Viscosity is you have a fluid, could be oil, gas, water, whatever, and then there are some molecules inside that one. Okay, as you increase pressure, these molecules are touching each other, causing, because the molecules move, causes more friction. So now you increase pressure, you cause more friction. Now for the gas, the molecules are way too far away. So that's why the gas viscosity is so low, because the molecule one here, there. For oil, the molecule one here, there. So too close to each other. Again, is a function of composition, pressure, and temperature for those, and unit is centipoise. So if you put the plot pressure versus viscosity or density, viscosity is here. As you increase pressure, viscosity goes down. So this is usually when I'm in front of audience, I ask them why viscosity goes down as you increase pressure. Because I mean, I already said that once you increase pressure, these molecules get together, so that causes more friction. Why? Because this is oil inside the reservoir. As I am increasing pressure, I'm getting more gas dissolved. So even this oil, because of compression, is going to get higher viscosity, but because I'm adding some gas into that, that gas is going to expand. So this is because of gas. The same story is because of density. The density gets lighter as you pressure it. If it is only oil, if you pressurize it, it's going to get denser. But it is in the reservoir. As you increase pressure, density goes down. So they have very similar trend, viscosity and density for oil. Now, this is a typical property that is just calculated from software. I'm going to show you the software at the end. So this is BO, remember, goes to the bubble point, and then from that point, it's going to decline because this part is liquid. This one is two-phase. If you look at the compressibility of the oil, is going to be high at low, and it's going to decrease. And the amount of gas in solution, which is RS, this is a bubble point. Above that is constant. Below that, as you come below bubble point, more gas comes out of solution. So you have less gas in solution. And then this is viscosity. Viscosity goes down, down, down until you get to the bubble point. So this is the maximum amount of gas that you can dissolve. From this point on is only liquid. You're compressing, so that's why it's going up. Okay. Let me see if I can show you. I am. Let me see if it opens it here. Okay, yeah, it opened it. Now, this is a movie that shows, let me stop it, that shows a well in the lab. You have a PVT equipment. I'm not sure how many of you guys have seen it. I mean, I used to have it in my graduate school that we were testing these things, but you know, I've seen it in so many other places. So you drop the pressure. Okay, so you drop the pressure. Let me go back here. All right. Okay, at this stage, the temperature is 157. So we're keeping temperature constant. Pressure is 5233, and we drop it. So the idea is that you look at when asphaltene starts. When asphaltene starts to come out of solution, you can see those dark. Okay, so let it go. Okay, it's getting a little bit darker. Okay, some drops come here, some more drops come here. So that's asphaltene. Okay, so that was asphaltene. So this is a piece of asphalt. Again, as we talk about it, asphaltene is more like a solid, and you do not want to have, I mean, the story of asphaltene, PVT of asphaltene is totally separate discussion that I didn't bring it here because that takes a lot of time. Huh? So you need to make sure that asphaltene does not form inside the reservoir, because if it forms, it is worse than gas condensate. It's going to drop. It's solid. So basically, you put some solid inside the pores. It's going to plug the pores. All right. So the technique is how to manage it that you stay above the AOF of the asphaltene, which is asphaltene onset pressure. They call it AOF. So that's another. Let me see if it is different. This is a different one, different oil. Starts out from 5600. Look at temperature, doesn't change, but pressure is changing. Look at that, it's more uniform, huh? So each one of them have their own criteria. Effect of API, oil gravity, and viscosity. So this is the API. If I increase the API gravity here, the oil viscosity is going to go down, obviously, because The higher API has it's lighter gas. It's lighter oil. These are some of the properties, and which I had, and I just generated myself. So I had these values, and I tried it with different APIs to see what is the mu by Bergman-Sutton technique. Now, effect of contamination. So the bubble point pressure changes, it decreases with increasing contamination. So if you have no contamination, the bubble point is going to be, let's say, 35, 80, 70. And as you add more contamination, the bubble point is going to drop. So this is the same thing like the Wyoming oil. Remember the Wyoming oil, the bubble point was like 95 because it is heavy. It doesn't have much gas. So now the impurity that you add into that one is just like stuff that you add without any gas in it, like heavier stuff, like some kind of oil that doesn't have gas in it. But the light oil had a very high, basically, bubble point. So the reason I put it here just to give you guys a hint that there's so many things that you need to be careful. Huh? Somebody cannot tell you, oh, the API gravity of this oil is 300 or 310. Huh? You got to make sure that that oil is clean. That's why when we test it with our downhole fluid sample and stuff like that, is we call it RDT, Reservoir Description Tool. We have all the stuff at down there. We have a pump. We keep pumping it, and then we are monitoring density. We are monitoring the gas oil ratio. We're monitoring everything. Once it gets to about 5% contamination, then we start sampling. A company, it takes longer time of pumping on. Sometimes we are pumping the oil from the reservoir and then dumping into the wellbore until it cleans. Some companies say, okay, 10% contamination is fine. Some places say bring it to 2%. So we pump until it is 2% contamination, then we take the sample. And then they take it. I mean, once we take a sample, we can give them the API gravity of that oil. We can give them the density. We can give them all the viscosity, gas oil ratio, bubble point. We can give them right there in downhole. We have a downhole basic like a PVT lab that does all of this. But again, these are not exact because you got some of these contamination. So when they take it to the lab, they test it, it's going to be slightly different. So now let's go to gas. For the gas, we got two main equations, Boyle's law, which says volume and pressure are reversed. If I have a sample of gas and I increase pressure, the volume is going to shrink. And vice versa. If I have sample of gas, I expand it, pressure is going to drop. That's called Boyle's law. The other law is Charles' law, which says pressure is related to temperature. Okay. And again, there's a mistake here on the number 39, is a mistake. Pressure is related to temperature if volume is kept constant. This is supposed to be volume. And volume is going to be equal to related to temperature when pressure is kept constant. So that means I have a constant volume and I keep the pressure constant. I only increase temperature. Okay. So the volume is going to expand. So now if I just combine these two laws together, it's going to be P times V divided by temperature is constant. Which means if it's constant, I can have a condition of, let's say, 1 atmosphere, a certain volume, a certain temperature. If I increase pressure, volume changes, and temperature I can change. So this is the relationship between these, and then R is the gas constant. Okay. So now P multiplied by V is equal to R times T. This is for 1 mole. But if I have a lot of gas, then P times V is going to be RT. If I have a lot of gas, then it is N. If I have 1 mole, then it is 1. But if I have more gas, bigger volume, it's called number of pound moles. And what is number of pound moles? There's the mass of the gas divided by molecular weight of that gas. If it is, let's say, methane, this is 16 divided by, mass of that methane divided by molecular weight of the methane, which is 16, all right? If it is air, this is going to be 28.96. You use 29. Now, this is for ideal gas. That means if I increase pressure, everything else is the same, volume is going to be decreasing. If I double pressure, volume is going to be 1/2. If I make pressure increase it by a factor of 4, volume drops by a factor of 4. But you can do it up to a certain amount. If you increase pressure more, then it is not, after a while, you cannot decrease volume by that ratio. If I increase pressure 10 times, volume is not going to go down 10 times. Maybe it goes down 8 times. Because now there are molecules that are resisting. I mean, it's not a sponge now. You can resist back, all right? So now this is called ideal gas equation, and then there's non-ideal gas equation. One of those equations called van der Waals equation of a state. So if somebody wants to solve for equation of a state, is this equation, which pressure, volume, number of pound moles, and some constant, or universal gas constant, and T temperature. All right. So now, so equation of a state for ideal gas, PV equal to nRT. For real gas, it is PV is equal to Z nRT. Z is that non-ideal factor. Okay, Z is, if it is ideal, then Z is going to be equal. It's called compressibility factor. So there's a lot of research and laboratory work done to calculate that Z. And Sandy did a lot of work on that area. All right, so N is equal to, as we said, mass of the gas divided by molecular weight of the gas. These are in field unit. Cubic feet PSIA, remember A, absolute. Temperature in degree Rankine, which is the degrees Fahrenheit plus 460. Then the R number is going to be 10.732. This is the unit of PSI, cubic feet per pound mole per R. Basically, the unit of this one is here to make this one balance. N is number of pound moles, M is pound mass, M is molecular weight, which is pound per pound mole. That means if I have 1 pound mole of methane, how many pounds would that be? 16. So now if I put the standard condition here, which is this equation, and some condition, if temperature is 14.696, temperature is 520 degrees R, which is 60 degrees Fahrenheit, then you solve for, because I have P, this is 1, I have R, this is 520, I solve for volume. Volume is going to be 379.4. Approximately we use 380. So at the standard condition, 1 pound mole of gas, any ideal gas at the standard condition is going to have a volume of 380 or 379.4 standard cubic feet per pound mole of gas. All right. So that means this is 1, this is 10.732, this is 460 plus 60, which is 520. This is 1 atmosphere. Then you solve for volume. All right. So now you can manipulate with some of these gas. We can calculate gas density and gravity. Remember, N is M over M. That's a unit. And then density is mass divided by volume. Okay, mass divided by volume. Mass is mass. Volume is going to be, you use the PV nRT equation. And then rho comes, you saw P goes over the MP over ZRT. All right, for this M, you put N times M, and an N cancel out. So the density of gas is MP over ZRT. I memorized this one because we had a professor, his name was MP Sharma. He was from India. So I never forget this equation, for somehow related to his name. Density of gas, MP over ZRT, right? And then unit is pound per cubic feet. So this is density, huh? Now specific gravity, again, for gas, specific gravity is related to air. How much heavier is that with respect to air? For oil is how much heavier it is with respect to water. So specific gravity is, you measure it, again, I put it here for you guys. It is at standard conditions. It is not at reservoir. It is not any other, at the standard condition. So rho G divided by rho air for the rho of the gas is going to be here, MP over ZRT. For rho of the air is going to be this, but this is, since this is standard condition, Z is 1, okay? And then temperature cancels out, pressure cancels out, then gamma of the gas is going to be basically molecular weight of the gas divided by molecular weight of water, which is 29, huh? Now, density of a gas, which is again me m over v, m, the same equation, mpzrt, and now zrt is the same thing, but for m, I can put specific gravity times 28.96. So rho of the gas is going to be equal to this number, specific gravity of the gas times pressure of the gas divided by zrt. So you can do it this way, or you can do it that way. Remember, this one, rho g, is at any condition. The rho g could be in the reservoir, could be in the wellbore. But when you talk about specific gravity, it is specifically at surface. Remember, I talked about the gas gradient. The gas gradient is basically density divided by density of the, basically from the density. You just divide and bring it to PSI per foot. So this is the conversion factor, 144 inch per square. So you just manipulate it for rho g. I put this equation, and it ends up to be 0.01875 gamma gas pressure ZT. So that's called gas gradient. All right. Now, if you have the gas gradient from the wellbore, remember you're coming up there, you're getting the pressure reading at any point. You plot it versus depth, you can come up with the gas gradient. So I have this gas gradient from the pressure data. If I have pressure and I know temperature, because temperature, we know the temperature inside the wellbore. Okay, if I have temperature also, and I know pressure because you're plotting pressure versus depth, on pressure versus depth here. So I have pressure, you have, any gauge has temperature. So I have temperature, pressure, and then I can, there are some techniques I'll show you later on to how to get Z. Then from that gradient, you can find out what is the gravity of the gas, gamma G, all right? So that helps you from that gradient to find out the gamma of the gas. All right. How about if I have a mixture of gas? Because if it is a single gas, methane, ethane, yeah, we talk about the equations. If I have a mixture of gas, then molecular weight would be average of the basically a mole fraction of each one of them times molecular weight. So if I have methane and ethane, if I have 80% methane, so this would be 0.8 times molecular weight of methane, which is 16, and 20% ethane, so it's going to be 0.2. Molecular of ethane, I think, is 30. So then you do the summation, you're going to be average molecular weight, all right? And then PC is the critical pressure, the same story, and the TC, critical temperature, and heating value, because each one is like 1 MCF of gas usually has about 1,000 BTU heating. So some people want to know, when I was in Saudi, they were asking me, okay, this is unconventional, how much BTU gas is going to produce? So they tested in lab. Actually, they give us the numbers, but roughly, if you do not have it, just use 1,000. Right? These are done in the lab. I'm sorry, the labs gives you the properties of each one of these. And remember that the one that I used for my calculation, it had a C1, C2. So if you put those, you have the molecular weight of C1, C2 all the way down, and then you have the mole fraction. So multiply by mole fraction, you get the molecular weight, and then sum it up. These are done very easily in Excel. You put it in a spreadsheet and you calculate all the properties of that mixture of gas. So now that you have the property of the gas, you can get something called a pseudo-critical pressure or pseudo-critical temperature. Sometimes they just use a PC and TC, okay? Which are, this is by Sutton, which is good for the specific gravity between 0.57 and 1.68, which is pretty good range. And then you, the function of gamma G, and then you can get the TC and PC, pseudo-critical mixture of the mixture and the pressure. So now that you calculate the pseudo-critical pressure, and then reservoir pressure is, let's say, 5,000, and then this is like 3,000. So the 5,000 by that one is called pseudo-reduced pressure. Similarly, pseudo-reduced temperature, okay? And then PC and TC are just like done as we talk about here, okay? PC and TC. You get those, all right? So again, go back here. I calculate the molecular weight, I calculate the gravity, I calculate the PCTC of the mixture, okay? Once I do that one, I have the reservoir pressure and temperature. I calculate the reduced pressure, pseudo-reduced pressure and temperature. Then I come here. This is the specific gravity of the mixture. And then this is the pseudo-critical temperature, pseudo-critical pressure. So if it is, let's say the specific gravity is 0.75, and then let's call it 0.8, it's easier. And then you can come here. If it's a condensate gas, then it is going to be like 440, 420, something like that. And then if it's a different gas, it's going to be there. Similarly for pressure, the same way. 0.8, you come down here, you read it for gas condensate well or for others, roughly about 650, 670, 665, something like that. All right. So now these are graphical, huh? Not software. So now from a mixture, you know the specific gravity of the mixture because you have the composition. You went down here, you can come down here, you get the critical pressure and temperature of that mixture because the mixture we call it pseudo, huh? If you have any impurities, as mentioned here, nitrogen, CO2, H2S, and they modify it, and if it is less than 5% is okay, not a big deal. And there are some empirical methods that can correct for those impurities, like Azari's correlation, Carr, Kobayashi, and Burroughs correlation, which presented. So how do those things happen? A pseudo-critical temperature for non-hydrocarbon content for each mole. So for each mole of CO2, you subtract 0.8. For each mole of H2S, you add 1.3. And nitrogen, you subtract 2.5. For the pseudo-critical pressure, CO2 add, H2S add, nitrogen subtract. So once you calculate those from this graph, if you know how much you have of these components, you add and subtract, all right? To get the combined, the true combined mixtures, PC and TC. Okay. Now that you have the PC and TC, and then you divide it by reservoir pressure and temperature by this PC and TC, you come with the reduced properties. This is called Katz and standing correlation, standing and Katz correlation. And then you can come on down here. So if they reduce pressure from 7 to 16, here is from 0. These are two segments from 0 to 8. Huh? So let's say pseudo reduce pressure is 3. Okay. Then what is plotted here is pseudo reduced temperature. So you come down here, pseudo reduced temperature is, let's say here at this point, like 1.82. Then you come down here, Z factor, you read the Z factor 0.9. So remember P multiplied by V equal to ZRT, all right? So now you got Z. So all of these calculations were done to get the mixture together. From that mixture, you get the critical properties, and then go there, get the reduced properties, come down to this Katz understanding, get the reduced property, get the Z factor. But that was the whole idea. So Z factor exercises, gamma gas, pressure, temperature, stuff like that. And then you use the Sutton, remember Sutton, where is it, Sutton? Sutton regression equation for PC and TC. Okay, if I use that Sutton equation, I am gonna get like 652. If I do from these charts, I'm gonna come up with 670, which is not bad. I mean, and then for the TC, pseudo reduced temperature, I'm gonna come with 390. From chart, I'm gonna read 408. And then based on that one, I get the P reduced, T reduced, and then Z is gonna be 0.96. If I use from the chart, P reduced, T reduced is going to be a little bit different. Z is going to be 0.98. So one of them is going to give me 0.96 for Z, one of them 0.98, which is all acceptable. So now isothermal gas compressibility is you use the same equation and then use the CG equation here. and you just play with that one. If it is, you just keep going with that equation. Because I just want to go a little bit faster to not bore a lot of, because some of you guys is late at night maybe. So you play with these numbers and you come up with the C reduced pressure compressibility is equal to CG times that pseudo-critical pressure. So this is very simple equation. And now the CG is equal to CPCR, and what you do is you enter the pseudo-reduced pressure, which you remember pressure divided by critical pressure. You go to the pseudo-reduced temperature. So let's say it was like 4, or let's say it's 5 on the pressure, and then it was like 1.8 here. Then this is going to be 7. So this is called pseudo-reduced compressibility, and then pseudo-reduced compressibility is this one, and then you have the pseudo pressure, which was like 4 or 5, and then you multiply or divide, and you get the density. All right. So this is from 1 to 8, and then this is the high end, which is like 10 and 15. But anyhow, so gas compressibility, reservoir pressure. As you increase reservoir pressure, the gas compressibility goes down because you are moving it toward liquid. When it's a gas, it's very compressible, but as you increase it, increase pressure, the compressibility goes down. And then there is one called BG, formation volume factor, which is volume in the reservoir, the same as oil. Volume in the reservoir, the volume at the standard condition. And then volume in the reservoir is going to be Z and RT over P. And then at the standard condition is Z at the standard condition, which is 1. N, which is the same, N cancels out, R cancels out. Temperature is 520 at reservoir. Standard condition is 14.7 here. You just plug these numbers, you come up with this equation for BG. You put TC at 520, for PC you put 14.7, you come up with BG, which is 0.02827, 2829, something in that range, ZT over P, all right? So 0.02829 to 0.827, something in that range, because depending on how you, if you use 14.7 or use 14.696, or how you approximate that. So this is one of the equations that you need to memorize and use it for the BG fraction. So now if you have T, temperature, you have P, pressure, you already calculated Z from here, from Cass understanding equation. So now you have a Z, and then you can get the BG. Why do I need the BG? Because if I have produced so much gas at surface, I want to see what kind of volume it occupies. You just multiply by that one. Now gas viscosity, again in the units of centipoise, and if somebody wants to know what is the RE unit, is going to be 2.09 times 10 to the minus 3 pound second foot square. And viscosity you measure in the lab, and then these are some of the correlation. Carl Kobayashi, Boros, or Lee Gonzalez, Iken. So Z and BG exercise, basically gamma G, pressure, temperature, TC is 428. You can go to that chart. Remember the chart that had PC and TC, PC here, TC on the top. So you read PC and TC based on the gamma G, and then reduce is you divide temperature by TC. Reduce pressure is divide pressure by PC, and then you go to the standing and Cass chart, and then you can get Z. Okay. Once you get Z, you can put in this equation for BG, and so the number is 0.00381 cubic feet per centimeter. Look at this number; it's very small. So that means 1 standard cubic of this gas in the reservoir is going to have a volume of 0.0038. Reverse it. So this is like 4 over 1,000. So it's going to have 1,000 divided by, let me see, 1, 2, 3, or 4. So it's going to be, so 1 cubic feet of gas in the reservoir, because 1,000 divided by 4 is 250, correct? So now 1 cubic feet of gas in the reservoir is going to have 250, over 250 cubic feet at surface. So it's going to expand a lot. This is reverse of oil, okay? Oil has more volume in the reservoir than surface, but gas is different. It's going to have so much more gas at surface compared, because in the reservoir it's compressed. Again, there's some correlation that you put the molecular weight and temperature, you come up with the viscosity at 1 atmosphere. and then you can get the pseudo reduced pressure here, pseudo reduced temperature, get the ratio, multiply by that number to come up with the viscosity. I mean, there are so many correlations. And then fluid properties for gas is basically, let me bring it here. Okay, so fluid properties for the gas, this is Z factor versus pressure. This is BG. BG drops significantly. And remember, the higher the pressure, the lower will be the BG. That means at this end, you bring it here, it's going to have more volume at surface. If the reservoir pressure is low, that means when you bring it to the surface, it's not going to be as much volume. And then down here, you got CG, compressibility. Yeah, we had this one before. At higher pressure, you compress it, you become like a liquid, so its compression is going to be lower. And then viscosity is the gas. You increase pressure, the molecules of the gas are going to get closer and closer. You're going to have more friction, so viscosity is going to be high. Gas condensate properties. Okay, so we talk about the gas. Now this is gas condensate. Remember, the gas condensate, you are to the, this is the bubble. Look at this one. This shape, this phase envelope is totally different. So each one is different. And so now this one is dew point, a critical point here. This is a fluid, gets to the bubble point, and then you, as you're coming down, you're getting more and more liquid out. So this is called gas condensate. Kamia Reservoir. Okay, so this is a certain reservoir in Africa, in West Africa. So now phase envelope for various hydrocarbons, I mean, dry gas, wet gas, the shape of it. Just look at the shape of it, how they change. Critical fluid, volatile oil, black oil, so they all change. So now if I have a separator gas condensate at equilibrium, inside the separator, inside the separator is one that you drop the pressure, you have gas above it, and then you have liquid below that, okay? So now you have for the gas part, you have a separator gas. For the oil, you got the separator oil, and then these are on the dew point side, and on the bubble point side, they have the same condition, have the same pressure and temperature. And this is the reservoir, sorry, this is the separator temperature and separator pressure, all right? So they are in equilibrium at where they cross. And now, but the reservoirs could be different. The reservoir is neither this, nor that, somewhere happened in the two. Now this is a little bit more critical is, I try to use this, in the reservoir, I was at this point. This is something I did. At the wellhead, at the choke wellhead, this was the condition. So pressure, temperature was a little bit lower because cooling down, huh? But pressure had dropped. From the reservoir to here, pressure had dropped. And there was a condition that we wanted to get a sample at the, I proposed to get a sample at the wellhead. Because once you go to the separator, it separates and I do not know what is the relationship. So if I can get it, this is the wellhead, this is the choke here, before the choke, and this is after choke. I can go and open the valve from this end, but what I needed to do, I needed to increase pressure to make sure that I'm above the dew point. So if you're producing here, at the wellhead, you're producing at point B, so you're in the two phase, it's not good, huh? So what I propose that we gradually lower the choke size. As I'm decreasing the choke size, I am increasing the wellhead pressure. I am decreasing the flow rate and I'm increasing the wellhead pressure. So once I increase the wellhead pressure, I'm gradually moving here, that I go, the fluid that is coming here before the choke is going to be single phase gas condensate. So there's so many different things that you can do. All right? I do not want to go too much into the details of it. It was very, very interesting thing that I did. And then, so what is the importance of the dew point? So this is a simulation that I did with a simulator. This is production time all the way to 12,000 hours. And then this is the gas, how much gas I can produce, flow rate, or cumulatively produce, the cumulative production. So if the dew point is 4,800, I can produce about, let's say after 10,000, I can have about almost 14 BCF, okay? If the dew point is higher, I can only produce like 11. So you can see having a lower dew point is very beneficial. Now, this is the dew point variation with GOR, which was another project that I did for one of the companies. So this is the RS, which is the solution gas oil ratio increases. And then this is the dew point pressure, that how they affect each other. And then this is temperature versus dew point pressure. So if I have a reservoir at a higher temperature, the dew point is going to be lower. Now this is the CO2, how CO2 reduces the dew point pressure. Remember, it is good to have a lower dew point. I can produce more. So if you add CO2, it's going to reduce it. And also CO2 can cover more of the condensate than methane. If you inject methane to maintain pressure or nitrogen, but CO2 is better, okay? But CO2, if you increase the pressure significantly, it's gonna basically become liquid, and then it's not gonna be effective in gas, but it's gonna be effective in oil. So we say that do not go above 0.45 psi per foot. And again, there's a lot of, for each one of them, I'm dropping a lot. So water properties, and the same as when we had gas, oil is dissolving it, the same thing with the water. Water inside the reservoir at a high pressure temperature, those conditions can have some gas dissolve in it. As the pressure releases, that gas comes out of it. And then density, as we mentioned before, is a function of salinity. If you have more salt dissolving that, the density is going to be higher. Temperature is going to decrease the density. Pressure is going to increase it slightly because water is almost incompressible. But salinity, salt, is going to increase it significantly. So you got to know the value of each one of them. And normally, formation volume factor of water is very close to 1. Remember, for the gas, for the oil, if it's a very light oil, it's going to be like 3.5. Normally, for BO, formation factor for oil, I use like 1.8, something like that. Light oil, I use higher, okay? But for water, it's like 1.05, something in that range. So we use correlation to get that one. And another, the salinity of chloride in ppm. If I have the chloride in ppm, because I give you sometimes that one, you multiply by 1.65, you can get the salt salinity in ppm. Seawater salinity is about 16,000 ppm. So there's some numbers to know. And these are a typical condition of a fluid. Let me see anything special here. Okay, look at this one. Initial oil viscosity is only 0.25. Look at that, 0.25. Oil viscosity at saturation conditions 0.21. That means maximum amount of gas. And this is only a 45 API gravity. And let me see what else I can find. Yeah, this is the water. Now look at that water. Water has 250,000 ppm. That's very high, very high. And then water gravity is 1.27, very high because of too much salt in it. The density is 1.2. Look at the viscosity. Viscosity of water is 0.45. Look at this one. Viscosity of that oil is 0.25. So this needs to be highlighted. Slide number, let me see what the slide is. This. Highlight viscosity. Okay, I'm putting notes for modification. I need to make this one bold, 0.25 and 0.45 for the viscosity of water. So you see that water is more viscous than oil. Isn't that funny, huh? Now, look at this one. I usually like to ask question, what is that one? This is at surface. You're opening the joint of the drill pipe, huh? You open that one, you move this one away. Now you move this one away, you get this one, huh? Nice round pebble. So I keep asking questions. Somebody said, oh, propan, somebody said this, someone said that. But since I'm not in front of you guys, And think about it, huh? This is salt. This is salt. Remember how much salt? 250,000. Remember the seawater salt is 16,000. I did some lab before and injecting some sodium and potassium chloride to improve permeability. I had a graduate student, and I think we went to like 25,000 or 28,000, that's the maximum that you could go with the lab. And you know, it's corrosive after a while. So now this is salt. This is the same fluid that I showed you here, 250,000 ppm of salt. You bring it here, you suddenly, because it's moving inside the pipe, but this is very nice and round, huh? So this is fluid property for water. This is the solution, RS, solution gas ratio of that one. It gets to the maximum at bubble point. The same thing, it has similar to oil because it has some gas in it, huh? And then compressibility, it goes higher. High compressibility goes lower. Why? Because that as it goes to bubble point, you get some gas dissolved in that. Remember? Gas can get dissolved in that water. And then you go below that, is only there is no more gas, you just compress the liquid. BW, formation volume factor, starts at 1.04, and with pressure, it goes to 1.02 or so. Huh? Remember, I told you that's the range, 1 point something. And then viscosity is dropping, and this is 1 centipoise. Huh? So this is roughly around surface. It's more than 1 centipoise because it has salt in it, because of the salt. Now, how much methane can be dissolved in water? This is a paper that I did, went to Journal Petroleum Technology in August 1998, was published. And I modified one which was available, but it was only up to like 4,000 PSI, 5,000 PSI. I increased the pressure range of these charts. Here is the temperature, and then with gas saturation, formation volume factor, which is BW versus pressure. So if your temperature is 180 and then pressure is somewhere here, 6,000-7,000, you come here, your BW is going to be 1.015. That paper was, the idea was producing, was a government project, DOE, Department of Energy, that you basically produce, there are some geopressure reservoir that has a lot of pressure, water at high temperature. North of California, they have a lot of those, geothermal, geopressure. So you produce it, you use the temperature, and then as you are releasing, some methane comes here. And we're trying to find out how much methane and stuff like that, and how should we make it profitable. And then here is temperature here, pressure there, and then again, solubility of methane. Solubility of methane in pure water. And that standard cubic feet per barrel. So look at that. At 180, and then this at 7,000, 7,000, you are roughly talking about 24. 24 standard cubic feet of gas dissolved in 1 barrel of water, which is not bad, huh? And then if you have some solids, stuff like that, it is going to reduce it. So 20% solid and 20,000 ppm of solid, then at that temperature is going to be 0.9. So whatever you get there, we multiply by 0.9 for that. Formation and effective. So we talk about the oil, we talk about oil, gas condensate, gas, water. Now let's talk about formation a little bit. Oops, I need to be here. And okay. I talk about this equation in the well testing part. So in the reservoir, remember I showed you one example of this one with oil. I assume it's oil because we had not gone this far. But now that you got to the end of the understanding of compressibility, the compressibility is not only oil, it's oil, water, gas, and the rock. Because if I pressurize a fluid, or if I take fluid out of a reservoir, so pressurize or decrease pressure, I am getting the entire rock expands. So let's say I produce from that. The rock expands, the gas expands, the water expands. So the rest of the fluid expands to fill it up. So they prevent the pressure to drop that fast. If it is a solid container and you take a little bit of the fluid out, pressure drops to zero. I mean, you can drop from, let's say you have a very solid cylinder of water in that one, you increase pressure to 10,000. You take few drops of water out of that one, pressure drops to zero because it's almost incompressible. But now all of these are compressible, and then this is also good compressible, like 3 times 10 to the power minus 6, but gas is roughly 100 times more compressible than these guys. So now remember this equation we had there, the amount of production of the oil that you produce is going to be equal to CT times area. This is from the compressible equation we had before. Porosity 1 minus saturation, delta P divided by that one, or MPBO is equal to N produced oil, total oil in place, total compressibility, and delta P. So now you can say, okay, if I have this much oil, 1 million, remember that 1 million barrel of oil, and I produce 10,000 of that one, and then CTE, remember before was like 3 or 4, and then 10 times 10 to the power minus 6, and then how much pressure drops. So now the pressure is not going to drop that much because now you got more of these fluids here. And so I basically repeated the same example there, CO, CW, CF, stuff like that, and with the saturations. And now CT is going to be 12.6. Remember that the first one we did, for the oil we used like 4. So now the volume of hydrocarbon is going to be AH, area times porosity per volume times 1 saturation, hydrocarbon volume. I have all of these numbers, calculate the volume of the hydrocarbon. The N at hydrocarbon in a stock tank barrel at surface is going to be VA, that one divided by BO. Remember, BO is the one that converts the volume from the reservoir to surface. So N is 22.34 divided by BOI, which was 1.25. Then I have, initially I have like 18 million cubic feet of oil. Then I put in this equation, MP in this equation, which is here. Then I produce 10,000 barrel, BO right now is 1.3, N is this much, BOI is 1.25, CT is 2, that's CT, delta P. So now you still get, the delta P is only 46. Remember before was like a big number, like few thousand, now it's only 46. So you can see that having these fluids in the reservoir is going to help maintain the reservoir pressure. So pressure is going to drop from 6,000 to 5953. All right. And these are the references. And what am I going to do? I am going to do this part. Okay. I am going to spend another 10 minutes or so showing the same software that I showed before. This is a well testing software called Sapphire, which is part of Kappa Engineering, is a French company. And this is the best software available in the industry for well testing. It's not specific for PVT, but the PVT modeling in this one is very powerful. And then the newer version that they have is even more powerful because you can compare so many different scenarios. And Halliburton was one of the first ones that companies that they got this software. I remember I recommended to use this one in probably 1992. And they have different programs for production logging, for formation testing, stuff, but this is for well testing part. So I'm going to create a, click here, this is called new, and then you can put the wellbore radius, Payson edge, porosity, whatever you have here, and then you can have oil, gas, water as your reference. So let's say it's oil, and then let's say I have gas and I have water as well. If I don't put any of these, it's gonna have oil in. Okay, so let's go to. I didn't check anything, so I go to this one, and then you can put the formation volume factor, viscosity, and total compressibility if you have calculated it yourself. All right, but if not, you can go to the advanced one. If you go to the advanced one, it shows you this is gas, this is oil. It doesn't show water. All right, so I can go back here now. Remember I told you I can go back here and include water. Okay, now that I include water, let's see. It's dead oil because because if I put water, it knows that I specifically put water, but it didn't put gas. it calls it dead oil. But if I put no water, it's gonna assume that this is not dead oil. So you gotta make sure that you're doing it, you put the phases here. So if you have them, then put it there. And again, you have different analysis, standard, non-linear, multi-layer, all of these are possible with that one. Formation testers, slug test, shale gas, all of these are there. Okay, so now let's keep going. So now I got all three phases of water, gas, and oil. So I can separately get the PVT for each one of them. You enter reservoir temperature, all right? So let's say reservoir temperature is 250, all right? Reservoir pressure, let's say reservoir pressure is 6,000, all right? If you have the gas-oil ratio, you can put it there, standard QV study. If you do not have it, then if you have other parameters, you can go back and forth until you match it, all right? This is how I match this one here. It's a little bit more involved, and I can show it to you how to get this one correct, because sometimes you do not have this one. Then you go click on the water. Water is simple. You either put the salinity, let's say it's, this is 10,000, so let's say it's 20,000. So let's say salinity is 20,000, or if you want to know what is the density or gravity of a 20,000, you can click on that one. It's 1.01, all right? Or let's say you have a 1.02 on the gravity, you want to know salinity. It's 25,570, all right? So let's go back here and put it 20,000. And then this is RS solution gas water ratio by Katz, Meehan, Ramey, Spavi, all of these guys, huh? BW is all of these guys, huh? McCain, Gould, Spivey, Meehan, stuff like that. CW, which is compressive, Dodson understanding, and okay, viscosity, Van Wingen, Frick, or you can use Meehan. So there's a lot of correlation. And as I mentioned here, each correlation is related to a certain oil. That guy was in Saudi, Middle East, he took the Middle East oil. The guy was in California, used that one. The guy was in Louisiana, used that one. So either you need to know which one of your oil is close to each one of them, or you can just do play back and forth until you match everything, okay? Normally, if I do not have any information, I pick up this here. When I want to do a really good job, I have time that I can spend some time on it. I have some properties, I have some values, and I match that one with a certain correlation. I just do it individually. I try Katz, okay, and then write down the parameters. I use Meehan, I use this one, Spivey, until I get the right correlation. And those are, let's say, RSW, BW, formation volume factor, CW, compressive of that one, density of that one, viscosity. At times, you know, because we said we are doing a downhole fluid sampling, and then we have the actually downhole PVT. I am seeing the temperature, I'm seeing the pressure, I'm seeing the density of the water, I'm seeing the density of that oil, or if it's gas, I see those. So now I try to match it. So one is, or you can just click on this one, it just gives you the match based on the pressure, temperature that we put. Okay. I have not done anything to the gas, anything to the oil, but only this water. So I can see that BW, CW, viscosity, and density. So look at this density, 0.97. So if we measured and then that density was 0.9, let's say 0.99, 0.9, let's say 0.98. Okay, so I know it's more dense. So that tells me what? That tells me I need to go there and put more salt. So now you can say, okay, I have a piece of paper, I write it down on that one. Okay, at 20,000 is this one. And then I can increase it to 22,000. At 22,000, it is 0.976. So I know it's a lot higher. So I go to 30,000. At 30,000, ooh, look at that, 1.1. So there's a certain range that I can put 26,000 at 26,000 is 0.97. So you see that point, almost 0.98. So 26,000 at 27,000 is 0.9800. So I matched on much one of those parameters. Okay, so let's say that one. And then you go to the gas. Same story with the gas. It's 0.7. If you know what is the gravity of that gas, you can do that. Or you can just, these are the Z factor. This is the BG, formation volume factor, compressibility of the gas, density of the gas, viscosity of the gas, and the water gas ratio. Or you can go to the main and click on this one. So for a gas gravity of 0.7, now you concentrate on this gas. Okay, these are the gases. So Z factor, viscosity, BG. So these are at the temperature of 250 and a pressure of 6,000. CG and rho G. If I know the density of the gas is 0.23 and let's say it's 0.24, then I can just come on here and change the gravity, all right? And let's go to the oil. I'll go to the oil. Oil is with respect to API. So this is API. You can also go based on a specific gravity or PSI per foot. I usually prefer API. Actually, this is part of the setting. You can go to the setting and say what to show. If the API is, let's say 40, again, I have different correlation, huh? Different correlation. So I spend a lot of time to prepare my model. Once my model is ready, everything is matched, then it doesn't take much for me to analyze it. So this is oil. Again, this is the bubble point of the oil. This is RS. Go to the bubble point, no gas. After that, compressibility, formation volume factor, density, viscosity, all right? Or I can just click on this guy. And now I have oil. So these are properties of the oil. Bubble point is 2476, RS is 561, BO is 1.3, CO is 8.9, mu is 0.5, and rho is that. So if one of these parameters is a little bit different, then you just go there and change the API. So maybe the API isn't that. So I play with that API until I match. And basically that's how it is. And then you say next. And then you put the saturation. So let's say saturation of the oil is, let's say 75. And water is 0.25. I'm sorry. .25. And then this is the rock compressibility. So if it's 3, the default is 3. If it is more than that, you can just put the number. This is CO, CG, CW, multiply this by that, water by that. Then add this one here to come up with a, you can go back here to my PVT again to go to a CT, which is 1.051 times 10 to the power. So it's actually like 10.5 times 10 to the power 6. Okay. So remember this was, you enter it, but now since I put the advanced one, it is showing my formation volume factor, my viscosity, the total compressibility. All right. And then you do the design. You can do the design or you can do the analysis if you have the data. Well, that does it. This is 2 hours. Sorry for those of you who didn't want to make it 2 hours, but I mean, this is like a 2 days presentation. I cut and cut and cut. The most difficult part is to keep cutting, keep cutting, keep cutting. And I'm ready to ask you a question. Again, I teach these courses to different places. I have done a lot of training when I was with Halliburton. Before retirement, I have done a lot of courses, different subjects that I can teach, all the way from fracturing to stimulation, production, even perforation, nodal analysis, optimization, you do gas lift, gas injection, second recovery, you name it, I have done it, and I'm expert in all of those. If any of you your company needs some of this training, I can come to the location. Or nowadays, if you want, I can do it online for like a week presentation school for your company or for your group. And well, I'm ready for questions now.
Thank you, Dr. Mehdi, for the great presentation, as usual. We can take 2 or 3 questions. Okay, someone asking about decline curve analysis. Do we use decline curve analysis for multi-layer reservoirs or heterogeneous reservoirs? Is it a good way?
Basically, decline curve analysis is not a real scientific things. If you remember from last time that we talked, I mean, it is declining, and then you suddenly stop the well for buildup or for something. You're doing a workover, so it's declining, and then pressure goes up, and then you stop producing, pressure goes down. Same thing with production. Production is declining, and you do acidizing or perforation, you shut the well in. Once you start the well, because now pressure has built up, it changes. You can do it on you can do it on single layer, multi-layer. You're basically putting all the production into a platform and see that. And most of these cases that I've dealt with, probably showed you, they're multi-layer. Some of those are from Algeria, and Algeria has like 4, 5 different, 6 different layers that they're producing. And maybe this well is completed in this layer, not here, but here. The next well is perforated not here, here, and here. So based on the condition and how many layers have perforated, it has a decline. So you're just trying to come up with a curve fit. It's a curve fitting. You curve fit that one. And if you go to that Excel has a lot of good curve fitting. Actually, not only that, but they can do forecasting. If it shows like that one, you can say, okay, forecast, let's say 1 cycle to the right, or 100 hours to the right, or 100 days to the right. It gives you, actually, it does. The ones that they calculated it for you, they showed you their calculation. I didn't go too much in detail of that one because this was a leftover from last time. And yeah, you can do any number of, it is unconventional, yeah, the decline is going to be faster. If it is high perforated, the decline is going to be less. High pressure, decline is going to be less. And then you go below dew point, decline is going to drop, production is going to drop. And remember, last time I showed you a few cases that was declining here, and then they start producing from another zone, and then they had like a baffle that broke, which is like an area that was not contributing, and it jumped. And so yeah, I mean, you can use any type, any size, any layers, anything.
Okay, a second question. You mentioned something about the critical pressure, critical temperature, reduced pressure. Whenever you are trying to calculate Z,
yes.
Someone asking what is the physical meaning of critical pressure and reduced pressure. He did not feel what do you mean about that?
Okay, let's see. Let me go to one of these cases. So if you have a PVT, and then you take that PVT to the lab, and here, let me see if I can bring it. Okay, let's see. I'm going to bring my slides to the right. Do you guys see this? Dr. Ahmed, do you see this?
Yes, we see it. Yes,
this is a typical, let's say this one. This is easy, simple. So for each fluid, you have a basically PVT diagram, okay? So once you have the PVT diagram of that fluid, and which is based on the temperature and pressure, there's a critical point for that point, for that fluid. And that critical point is, to the left of that is liquid, to the right of that is gas, all right? And then the gas has different types of gas. The oil has different types of oil. If you are way down here, which is low in temperature and low in pressure, you could have asphalting. I'm not showing any of those asphalting stuff here. You could have an asphalting situation. And then, so now if this is the oil, and then you get to this, you drop it here, this is called your bubble point. So this is how we call it bubble point pressure. And so for this oil, it has a critical pressure, and that's a critical pressure. Remember, I showed you a case that you have a two-phase at the separator. You have the separator, you have the liquid and liquid here, and gas, which is liquid is oil. Your oil and gas, they are in equilibrium. So there's a separate phase envelope for the gas, and then there's a separate phase envelope for the oil. The oil, which is on the top, the top part of that is liquid. The bottom part of the gas is gas. So when they cross, that is your separator condition. So at that separator, so you can see that the situation changes a lot. So you have a critical pressure. So for this oil has a critical pressure. If the oil is different, then you have a different critical point. So the critical point is a function of basically the function of, let me see, bring it here, composition. I think we had a critical condition here, which is that one, probably this one here. Oh. You see that specific gravity of the gas changes, you got a different critical pressure and temperature. See that? So the critical pressure, this one is critical temperature, could range anywhere from 350 to that one. So each composition has a different phase envelope and it has a different critical pressure. So you need that one. Once you know that one, then let's say reservoir pressure, let's say critical point is 3,000 and then your reservoir pressure is 6,000. So you divide that pressure by this 3,000, you come with the number 2. So that's called reduced pressure. And let's say your critical temperature is 100, in this situation is 650. This is degree Rankine, huh? Or sorry, is 500. So if let's say temperature is 500, and then your reservoir temperature is 250. So now your reduced temperature is going to be 0.5, reduced pressure is going to be 2. You just go to Cat's understanding, you reduce pressure and temperature, you get Z. The whole idea is to get Z factor. And this is the oldest style. This is the style that I grew up with, if you want to know the meaning of that one. But nowadays, you do not need to do that. Nowadays, you use this, huh? Nowadays, you just use this one, go to the PVT part, and you generate it, and then you try to match it, and you assume that the software is doing the right job. I mean, you assume that these guys know better than you do, and then you trust them, and then you come up with the match the values, all right? More questions?
Yes, the last question. Is it any other technique to calculate Z except this one you explained?
Yeah, I mean, the Z factor for this is Z factors for the gas, huh? Z factor is, this is the most popular one. Katz did a lot of work. I mean, when I was in Iran, he came to Abu Dhabi. The university that I went to was the highest and the toughest university to get in. He came there for some kind of work on teaching Katz. He did a lot of work in gas, and Standing was also very famous in this thing. So I mean, look at this. These guys, they kill themselves to come up with these charts. I mean, it's so difficult. And so they came with these correlations, you know, like this kind of correlations that we use here and there, and we talk about it. So this correlation that you see here, they had thousands of different scenarios to come up with one correlation. And now those correlations and those equations are used into models. So these models are basically on those correlations. And when you go to the PVT, there are so many correlations for BO. There's so many for compressibility or viscosity. So you can click on those and come up with numbers. Yeah, I mean, as I told you, once you go to this one and go to that one and go here and click on this one, if you're interested for oil, and then look at that, the bubble point. Remember, we did the standing, huh? We did the standing one for, this is about oil. He did a lot of work, but I mean, you can, Vasquez did work, Biggs did a lot of work. I mean, glass of volatile. I mean, sometimes I found out that the glass of volatile matches my oil. Glass of non-volatile matches, or Lasater standing. So these are different, all different correlations. So there are so many correlations of it. So you're interested in gas, calculate the Z factor, you click on the gas, all right? For the Z factor, look at the drum chuck. Biggs and Brill, Hallan, Yarborough, Standing, and Drawn Chalk. It's not ground chalk, huh? It's not the meat, huh? Drawn chalk, or from BG. I usually find the default values are the best one. Or Lee, the guy in the A&M University, Carr and Japanese guy that did the work. And then BG, you can use any of these. Okay, so yeah, there are so many correlations. And then some oil matches this correlation, some oil or gas matches the other correlation.
Okay.
But if you do not know it, just use the default values. If you do not know what kind of oil you have, just use whatever this guy says, because these are the most popular. If you know the parameters, then you can fine tune it. Remember, this is oil. For oil, you have, this is for your oil, huh? I usually, because we do the downhole sampling and I know the downhole density, I use this downhole density to match. All right? And then come up with the bubble point.
Okay, so thank you, Mehdi, for the great presentation. You always do a great job. So I appreciate being with us today. And, you know, I get many complaints from students asking, is it the last time we will see, you know, webinars for Dr. Mehdi? You know, I told them I will give you a break for maybe 1 month.
Well, I mean, on one hand, I have so much experience, so much knowledge that I want to pass. On the other hand, I got so many other things that I need to do here. But if somebody has told you any of these, you're working for a company, the company, they can approach me, then we can work up with a class for a student. I mean, when I was in Algeria, tell a few funny story. I was reviewing the wells and coming with production. So we had a field, and then we look at each one because we had several of us, we divided. But as a reservoir engineer, I had to write the final report, because everything was in a PowerPoint. We had a geologist over there, we had a petrophysicist, and then we had a production guy, fraction guy. So we had all of those guys. We look at everything, I get all of the information, and I do the final, put everything together, come up with an analysis. And then they found out that I have a PhD and I had so much, so the world got around that Mehdi is very knowledgeable. So now they send some of their graduate students that was working on getting their masters in from French university, different university, and graduate got a few of their master's students, and I gave them projects. So I ended up having like at least 3 or 4 of the guys working for Sonatrach over there. They did their dissertation with me. And the same thing when I went to Saudi Arabia, the manager from the first day, once he found, because they checked they refused a lot of resumes. And then my company, Halliburton, told me, Mehdi, you got to go to Saudi because you have experience in unconventional. So the manager had looked at them, and then he told me the first day, Mehdi, I want you to come to my office every day during lunch and give me 1-hour lecture. And then he also sent some of these students that they were from the studying US and Europe, and he sent it to me, I give them some projects to keep them busy. And not that as much in Kuwait, and Kuwait was basically working on production stuff. But in Algeria and Saudi Arabia, I dealt with a lot of these students. And I enjoyed, I enjoyed.
Okay, thank you, Mehdi, and you know, thank you for everybody watching the webinar, and we will see you next week. Thank you.
Already.